Welcome back to Ontology Talk. I'm Adam Pease, and I'd like to do a set of follow-ups to my recent video on understanding different logics by providing some detail that there really wasn't time to fit into the video that was already getting a bit too long. So let's just look at a couple of the problems that I explored on that video that are drawn from Jeff Sutcliffe's TPTP, Thousands of Problems About Theorem Proving. And the first one that I went through was a simple puzzle in propositional logic. And so if you download the problem set from TPTP, you can just go to tptp.org and get it. And this first one is puzzle number 4-1. I presented the English text, which is repeated here in the problem format. All these problems are very well structured, very well documented as to their origin and so forth. Here there's a specific bibliographic reference to Lewis Carroll. All the comments in this file are preceded by a %sign, and we get down to the actual meat of the problem here. And I thought I should just take a few moments to try to explain, give a quick introduction to TPTP syntax. So the first thing that you see in a TPTP language file, the first thing you're going to see is the type of the statement that is being shown. So here it's CNF, it's conjunctive normal form. And the next thing you see in a given statement is a name. The name is arbitrary. If you've authored the file, you can give it whatever name you want. It's not actually strictly required, as far as I know, for that name to be unique in the file, but it's certainly beneficial for it to be unique so that you can track back to your authored version later when you see a particular proof. The next thing that you find is going to be a keyword that describes what sort of statement it is. If it's axiom, that's generally what you use for things that you author. And if you see a keyword in this place in the proof, then you'll see a couple of different keywords, and we'll get to that when we cover the proof output. Another keyword that you'll also see is conjecture. We'll get to that at the bottom of this file. So there are probably only two keywords that you need to worry about: axiom and conjecture. And then you see the formula in TPTP format. These are all valid prologue syntax, which is a combination of infix and prefix notations. Logical operators are infix, and your user-defined relations and functions are going to be prefix. Also, with prologue syntax, you have capitals are going to be variables, and lowercase things are non-variables, they're just terms. Here we see a disjunction. So the vertical bar, just like in many programming languages, stands for or. That's the or operator. The tilde is the not operator, and an ampersand sign, although we don't see it here in any of these statements, is the and operator. So kind of mimicking Java, except Java uses the doubled ampersand and the doubled vertical bar instead of single. So here this says that it is true that not dated or on blue paper. You have to balance your parentheses, and then every statement is ended by a period. Again, valid prologue syntax. Pretty much the same sort of syntax here until we get down to the end, where we see another keyword, hypothesis. I'm not actually all that familiar with how that is different than axiom. It seems, as far as I know, to have the same function as just axiom. It's a statement that you provide. Maybe Jeff will give a little more detail, or I can dig up some more detail for everyone. But for now, let's just treat it as axiom. And finally, you can have either conjecture or negated conjecture. If you just type in the conjecture, the systems, the theorem provers, will actually do the negation for you, because we're doing negation, proof by negation or proof by refutation, where if you ask a query, then your query is negated and the system attempts to find a contradiction between the negated version of what you've asked and everything else that it knows. So you can go ahead if you want and just negate your own conjecture, and then it doesn't need to do that step for you. So that's what a typical simple propositional logic file looks like, using just this conjunctive normal form, because for propositional logic you don't need anything other than the conjunctive normal form language. That's the least expressive language in the TPTP family. And then for this file we can go ahead and execute a theorem prover on it. So let's take a look back in where I used eProver, and we'll grab that command. Okay, so here is the command that I used, and we'll just copy that, and we'll call this particular puzzle 04. Okay, there it is. I should take a moment to explain what we're doing here with eProver. On the links to my last talk on different logics, I also included in the comments section where the URLs where you can download the eProver content. It's on GitHub, and the compile takes a little while, but it's very simple. It's just a couple of make commands. And E has a lot of options. I'm not going to go into all those options here. I don't really use very many of those options. This is my standard configuration, where I select auto schedule. That just means sort of pick your best option for finding a good proof. There are various ways to direct E, direct its search process, and they can get quite complex. They're very sophisticated. There's a lot of stuff there for people that are interested in theorem proving as a discipline, but if you're just interested in getting an answer, getting a proof to a particular problem, I would advocate just using autoschedule. Then it takes care of all of it for you. It's a really nice parameter, so you don't have to worry about things. Then there's a command to say specifically, I want a proof. The theorem prover is a little bit faster if you don't ask it to give you a proof. But if you want to see how it did what it did and really validate, in fact, that you're getting the kind of answer that you thought you wanted, well, then it's a pretty good idea to select this proof object option. And then you get the name of the file that you're going to be doing a proof on, which is what we were just looking at. So if we run, it runs blindingly fast for this very simple proof, and we get the proof that I was showing in my last talk. And let's just walk through it briefly. First, with this set of options, it gives you a lot of sort of background meta information on what it's doing, things about the machine that you're running on. It tries to take advantage as much as it can of the hardware that you have, and then it regurgitates the file that you've given it. And if you're lucky, and if you've created a problem that is solvable, as this one is, it tells you proof found. And then it gives you that actual proof. And the proof starts by really just, again, regurgitating all the things you've told it. Right? And you can tell that because for each one of these statements, as its last argument to the prologue relationship CNF, it's given you a file keyword here, and the specific file, and then the name of the axiom from that file. So here we've called it with puz004-1, and that's what it's telling us. And it tells us that for this first chunk of a number of statements, 9 or 10 statements, something like that. And then it starts telling you about all the axioms that it's actually picked for the proof. So here, this first one begins with "Dear Sir." It's essentially just copying this statement and it's renamed it. It has this incremental, very simple naming scheme. It's automatically come up with this first argument as its new name for the proof, or the new name for the statement. And again, it's just an axiom. It's something that you've authored, as well as the hypothesis is something that you, as the supplier of this file, have authored. The first real interesting statement in the proof that we come to is marked plain. Plain just means that it's plain output. The system has created this deduction based on the rules of logic for this particular logical language, propositional logic, which is a subset of first-order logic. And it's, gives you this label, so you know it's something that's been deduced. It deduces this third argument to the CNF relation. This is the entire formula. In this case, it's a very simple formula. It's just one proposition, one propositional variable, if you will. And then it tells you, how did it get it? Well, it did some kind of inference. And this inference was a result of combining steps 11 and steps 12. So let's look at 11 and 12. So 11 says, either it's true that begins with Dear Sir or not by Brown. And then step 12 says by Brown. Well, if you combine those two things, not by Brown and by Brown annihilate each other. You've got negation. Now, if you know by Brown, then the disjunction of anything with the opposite of that term is going to be just the first thing. So you wind up being able to conclude begins with Dear Sir on the basis of by Brown and not by Brown, kind of annihilate each other. Another way of looking at this, as I mentioned during the different logics presentation, is that this is also essentially a rule, right? It's not begins with Dear Sir implies not by Brown, or if you reverse it, not by Brown is a disjunction, or of not by Brown begins with Dear Sir. If you reverse this, you can actually say instead, by Brown implies begin with Dear Sir. And you know by Brown, therefore you can conclude begins with Dear Sir. Right? That's just modus ponens basic reasoning. And then essentially for this very simple proof, you get a lot more of the same. For everything that's marked plain, we usually see that there's just two formulas that are antecedents. So here is 13 and 14. Let's take a look at 13 and 14. So we get not begins with Dear Sir or not in the third person. We know begins with Dear Sir. Therefore, we must be able to conclude not in the third person. And that's exactly what we do conclude here in step 16. And so this continues on until finally we get to the conclusion, false, a contradiction, which is a combination of steps 27, 28, and 29. So let's look at 27, 28, and 29, which is we have dated or not on one sheet. We have not dated. Therefore, we can conclude not on one sheet, and we also have on one sheet. So we're left with not on one sheet and on one sheet. That's a contradiction, so we can conclude false. We have a refutation, and we're done. So that's how to read a simple propositional logic proof and execute E. Thanks for watching. I have future videos planned for proofs with Vampire and Leo 3, and I hope you'll join me then.